Today we will discuss how to optimize blast furnace operation in a simple and practical way. Blast furnace running is not only experience based work, it is also a system of many connected variables like pulverized coal injection, blast temperature monitoring, burden quality, and consistent and stable fuel rate. So in this session we will learn three things. What are these? One by one we will look into. So the first thing that we are going to focus is that what are those main parts of an optimization model? What are those factors? So this is the most important part of our study. The second is how the furnace data behave, like a peak, peaks and valleys, how they, where we get the best value, where the performance remains best. So these sort of things answer we are going to derive. And third thing is how the GRG non-linear methods helps us to find the best operating point. So our aim is simple, get the best furnace performance from every kilogram of raw material and every unit of energy. So now our moving forward towards our next slide, which is about optimization. So optimization is something we already do every day. Every day we are doing. So in the kitchen we try to get the best test with the less time and effort. In travel we choose the best route to save time and fuel. In the blast furnace we do same thing. We always try to get a stable operation, low fuel rate and good hot metal quality with the minimum cost. If we reduce coke too much, as all operators know, the furnace may become unstable. If we overcorrect the burden, cost also goes up in these cases. So optimization means finding the best balance within the cost and without deviating the operational norms. So as you can see, every optimization model has a three main parts. So objective function, which talks about what we want to improve, like lower coke rate or higher productivity. As far the variables is concerned, the operating parameter we can change like PCI rate, blast temperature or moisture constraint. The limits, constraint basically the limits we cannot cross, like a flame temperature if range, the top gas temperature or hot metal quality. So this is important because we cannot change furnace setting freely. We must improve performance while staying inside the safe and practical operating limit. So this is the challenge. Coming to our next slide, so that is already show that when we change one operating variable, the result does not always change in a straight line. In many cases, the furnace response is very, and most of the time it's non-linear. That means the data looks like landscape with a peak and falls or peak and valleys we can say. So one point may look good, but another point may be even better without a proper method. So we may stop at a condition that is only acceptable, not truly optimum. So such analysis need to be done. Coming to uh, our next slide. So in this particularly here, in the theory the best point may lie outside the actual operating limit. So that is why the constraints are very important. For example, blower capacity, flame temperature, slack chemistry, top gas temperature and sulfur limit can all restrict the final solution. So the real target is not the theoretical best point. The real target is the best point that is safe, stable and achievable in plant condition. So This is the importance of this message. So these are the different optimization method as shown in the slide. So linear methods are fast, but blast furnace operation is usually not linear. For smooth nonlinear problems, GRG nonlinear is a suitable method. Microsoft and Frontline both describe GRG nonlinear as the method for smooth nonlinear models. Trial and errors can also be used, but it is slow and less reliable when many variables interact together. So forever, there is no one permanent definition of optimum blast furnace performance. The target changes according to plant needs. So sometimes the goal is minimum coke rate, sometimes it is a maximum production. In some situation, goal may be minimum cost or lower CO2 emission. So the optimization model must be flexible. The furnace target should be match the current business and operating priority. Coming to the practical optimization where it becomes useful only when we connect it with the actual blast furnace parameter. For example, objective function, that is the total fuel rate or productivity. Variable like PCI rate, burden distribution, slag basicity, blast temperature and constraint like flame, top gas temperature, hot metal silicon, sulfur, permeability limit, etc. So these makes the model practical. It helps engineers, operators, managers talk in the same language. So coming to our practical way to do this is by using a Excel solver. In this slide, this we try to give the message. So in solver, we define the objective cell, the changing variable cell and the constraint. Then we select GRG nonlinear as the solving method for smooth nonlinear problems. GRG helps find a locally optimal solution, which means the best solution near the current operating region. So instead of guessing setting, we can use a structural method to decide the best operating value within the real plant limit. So optimization means finding the best blast furnace operating condition within actual plant limit. So with a clear objective, correct variable, proper constraint and GRG non-linear solver, we can improve performance in a more scientific and reliable way.